Hey guys, how you doing? I'm Mike Aubrey. I'm the host of the wcUAV Challenge webinar series, and so with us, the the lady in charge, Princess Aaliyah, the coordinator of the challenge. Princess Aaliyah, thanks for being here, and we have our guest today, Mark Page. Mark, thank you for being with us today. So, for those of you guys who are airplane enthusiasts, Mark actually was one of the co-inventors of the blended wing aircraft. He has 18 years experience. He was working for McDonnell Douglas and Boeing when he did that, but now he's the VP and chief scientist of his own company. And I'll let him give his own introduction, but he's going to be sharing with us some of his experiences actually in that space. And I'm super excited to be on this webinar learning with you guys as we're going. So Mark, thank you so much for being here with us today.
Oh, well,
Yeah,
thank
tell
you
us a little
guys
bit
for
more about
for
yourself.
inviting me. Yeah, so that's right. I was 18 years at McDonnell Douglas Boeing, did the blended wing body, did prop fan stuff and all kinds of advanced airplane things, and then got the racing bug, went a little bit insane to be honest, and worked for Dan Gurney's All-American Racers doing 850 horsepower open wheel race cars, going 250 miles an hour, insane stuff. Did that for 3 years, and then 12 years at Swift Engineering, doing much the same, but with NASCAR and with funny cars and all kinds of race cars and supercars, but also did created a blended wing series of UAVs while at Swift. The Killer Bee and Bat, and we'll talk about those. Also did the
Wow.
Eclipse Concept Jet, which was a piece of paper to first flight in 200 days, very exciting program, and now we're doing those same sorts of things in my own company.
Wow.
So with that, I'll go ahead and get started, I guess.
This is going to be fun.
All right. So we're going to talk about what makes blended wings suitable for UAVs. Now, I want to acknowledge first NASA Langley, Boeing, Swift, Northrop, and Raytheon, who all contributed to the advancement of either blended wing technology by itself or the use of that technology for UAVs. And everything you're going to see is of course, unclassified, unrestricted. Virtually all of it's in the public domain already. So our team over here at DZYNE, and we're in Irvine, California, a small but growing company, about 40 folks. These are the vehicles that we've designed, and when I say we designed them, we designed them. So it's both a blessing and a curse. You get to do cool stuff, but it's all on you, and you show up on race day and you can't be late. So those skill sets naturally served us well doing advanced airplane projects. So what we do at DZYNE is we do concept development all the way through low rate initial production. We've got guys who go out and play in the desert and do flight testing. That's a hoot. And then we actually operate these systems ourselves, but we also have a big emphasis on styling and ergonomics. Strangely enough, for a technical company, not surprisingly, people seem to like pretty things. So doing stuff that's pleasing, both when you approach it as a product and just simply look at it, in our mind, is a way to get things sold and keep them sold. So I'm going to go way back in time here. This is 1988, and the chief scientist at NASA, Dennis Bushnell, asked this question: hey, could there be an aerodynamic renaissance for the long-haul transport? Here's why he asked that question. 1903, the Wright brothers create the airplane. A mere 44 years later, we've got pressurized tube and wing airplanes with swept wings going near Mach 1, jet engines, all the things we think of today as modern. 45 years later, there's the A330. And there were many advances, but all these advances were small evolutionary increments, and the pattern of the vehicle hadn't changed in all that time. So we were charged by NASA to take a look at some alternatives, and we had some notions on blending that we thought would be suitable to make a new species of airplane that could help. So what I'm showing you here is, if I got, back then, NASA asked us to come up with a 7,000 nautical mile, 800 passenger transport. If I put 800 people in the normal volume they have in an airplane and put them in a giant sphere, that's what it looks like down in the lower left. The 7,000 square foot is a area of a sphere that would hold everybody, perhaps not comfortably, but would hold all the people to do what you normally do in an airplane. Obviously, that's not going to go near Mach 1. That's not going to go 80% of the speed of sound flying through the air. So we all know the upper guy, the streamlined options, we're all familiar with the cigar. That works great. It's slender. It's very low drag. And more importantly, when I pressurize it, it's like a balloon. You know, I inflate it, and now all the tension, all the structural loads are principally tension, and most metallics are great in tension. Even carbon composites are great in tension. Compression, shear, and bending is when things get into trouble. So down below, however, I could also wrap that same volume with in a Frisbee. And remarkably, the surface area is almost the same. It's a little bit better, but basically the same. The issue, of course, is for transports, if I want to pressurize it, this isn't a favorable shape. I'll have to have bulkheads to resist turning that thing back into a sphere when I pressurize it. But you can see that if I change the concept for the fuselage, I can realize a small reduction in surface area. Why do I care about surface area? That's friction drag, and every square foot of surface area is structure I build. Typically, surface area of an airplane weighs, believe it or not, between 2 and 3 pounds per square foot. That's a lot. So we've got to find ways to reduce that, and then, of course, the friction drag. But here's where the magic happens. If I take a wing, same wing for both airplanes, a tube and wing airplane and a blended wing airplane, and I mate it with the fuselage, I get a little magic. The fuselage on the tube and wing conceals part of the wing. Now the wing's lift, believe it or not, is carried over on the fuselage pretty effectively. So the fuselage doesn't kill the lift that much. And the fuselage hides a little bit of the wing. So some of the wing lift I get almost for free. But when I have a blended wing Frisbee down below, I hide a huge amount of the exposed wing. It's just that simple. That is basically all there is to blended wings, is that I'm taking that cigar and I'm going to squish it, preserving volume, into a shape that reduces the total surface area of the system together. So now I've got a 20% reduction in friction. When I integrate the engines, I get similar benefits. When I integrate the tailplanes, I get even more. So now I've got a third less surface area on the airplane, because this airplane doesn't need a very large tail group, because the inertias are much smaller in pitch and yaw, and the variability in load, nose to tail, with that long fuselage is significant. So I need a big, powerful tail to balance the different center of gravities. I can do that very easily with control surfaces on the wing for the blended wing. So that's the essence of it. Let's look a little bit more into what that means structurally for the airplane. So on the upper left, I'm showing a cross-section through the airplane where I've got the weight of the airplane in red pulling the airplane down, and I got the lift on the wings holding the airplane up. And if I imagine if I had a red arrow pointing down with a blue arrow pointing up that was equal everywhere across the span, there would be no bending in the structure and no shear. In other words, the structure, I don't need structure. If the applied load in lift and the inertial reaction are perfectly equal, there's no stress in the structure. Of course, that isn't reality. I always get something. And because I have the mass concentrated in the middle, I get very large shears and bending moments in that wing structure right at the side of body. But look to the right, you can see a blended wing has an advantage, which is that it distributes that payload more consistently with the lift that carries it. So now as I move from wingtip to wingtip and ask how much shear and bending moment is in the structure, it's quite dramatically reduced. Another way of looking at it down below is you look at the tube and wing and look at the mass that the airplane must bear in red and its loads lengthwise, and I've got the lift being borne spanwise. So the structural load path is very long. A unit of lift in the wingtip going to lift part of the weight in the tail, you can see that load path is very long. That integrates up into a lot of structural weight. Blended wing, they're just more aligned. Aerodynamically, This is where you get some really cool magic when you're talking about a transonic airplane. So some of you, so this is a little bit of egghead stuff for the aero guys. So I apologize, but let's just say this. If I want to go near the speed of sound, like all of our airplanes, when I'm in a 747, I'm going like 0.85 Mach, 85% the speed of sound. Well, any old airfoil on a wing just can't do that. Or stated differently, if I want to fly that fast, I have to limit how much lift I carry, or I have to limit how thick the airfoil is, because that thickness causes the air to accelerate. So I have to give up. I can't have thickness and high lift. I have to distribute them between those two demands. So in this case, when I look at a blended wing, and tell me if you guys can you see my cursor okay?
Can, yes.
So here is the lift distribution on the airfoil. Where did that come from? Well, here's the lift on the whole airplane. Some of you may know that optimum lift on an airplane should be shaped like an ellipse. That's true if there's no structure included. When I include structure, it shouldn't be an ellipse, it should be slightly pointed ellipse. It's a little like halfway between a triangle and an ellipse. So this is an optimal aerostructural shape for the lift on the airplane. But you can see that out here, the chord, the length between the leading and trailing edges of the airfoil, is very small compared to in here. So the pressure loading, how much lift I'm carrying per square foot, is much higher on the outer wing, that's this yellow line, than the pressure loading in the middle where there's all this chord. Okay? But the cool thing is that because I have so much less pressure loading here, I don't need it and I don't want it. I don't want to carry extra lift on the center body that I don't want because it's not an ellipse shape. It'll make more vortex drag. It'll make more tornado drag, if you will. So I've got two things that make drag on an airplane. Half my drag is vortex drag. It has to do with how close this shape is to an ellipse. Half the drag is friction drag. That's just the wetted area, the upper area and the lower area added up, that's friction area. So when I get to have such a low lift level, lift pressure coefficient, if you will, in the middle, that allows me to go thicker. Well, guess what? That's where I'm putting payload. I want to be thicker. So you get this really nice aerostructural optimum where the large chord allows me to have low lift, and that's cool because I want large chords because I want tall people and cargo in there, and I can have both of them. Structurally, the airplane's very different. The outer wing looks like any other jetliner. But if I go into the center here where the fuselage is in pressure vessels, I have to cut the airplane into bays, and I have to have these members here to take the pressure loads. And you can see here is a slice of half the fuselage. So there's the center line of the fuselage. That's the nose. The wing's been cut off. And if I pressurize it, right, it's going to pillow. So we have to size the structure so that that pillowing is minor, is small, and I have to pay a price for it. I don't get it for free. Okay, it is heavier than a tube and wing cylindrical fuselage in here. But as a wing, it's wildly less heavy than the wing of a 747 in here because it's so deep and thick, the skin stresses are very low. We tested it back in '97 at the National Transonic Facility for a high Mach number, and we were very thrilled to see that our predictions in blue and the actual measured drag in red were so close. And by the way, the test showed a little less drag. We got stellar lift to drag ratio. That's the aerodynamic efficiency. We also tested at low speed to make sure that the airplane behaved properly. And you can see here we also had good correlation between our tests and our predictions. And we embarked then on designing a jetliner. This is what we call the so-called second generation BWB. This is our big initial NASA contract. And if you're going to be honest, you've always got to compare yourself to what the best conventional could do. It's not good to just draw an airplane and think it's better and argue that it's better. You have to prove that it's better with a fair comparison. So we had a team of guys using the same tools, but separate team developed the airplane here. It had an all-flying vertical tail. It had relaxed static stability. It's an all-carbon airplane. It was a double-decker. It had some benefits there. And we did the best tube and wing we could and then asked ourselves, how did the two compare on the same mission? This, by the way, is what the interior looked like. you can see that basically it's a bunch of little, it's like half 737s in length. So that center aisle there, by the way, on this airplane, this is an 800 passenger airplane, not one that Boeing would ever have built. The biggest one they would have offered would have been about 500. But in any case, NASA wanted a big airplane. But nonetheless, you can see that these bays are sort of like a 737 or 757 fuselage. Only difference is, if you've ever been in a 757, you know it takes forever to get off the thing because it's so darn long. Each of these bays is about a third as long as a 757 bay fuselage. So you get out to the front doors right away. You have multiple ways of exiting the airplane. So even in an emergency, the blended wing has a stellar emergency egress speed compared to a tube and wing. So it might at first seem like, oh, wait a minute, isn't that harder? It's actually much, much better because I've got short cabins, I have a common cross aisles, and then then one person can't stop an entire tube of airplane. One person can only stop now a small fraction of the airplane's capacity from getting out. Okay, so when all the dust settled, here's where we were back in the early 90s looking at this airplane, 7,000 nautical miles. It was about an 800,000-pound airplane, big wingspan because it likes that. Now that it's got that center body in there and the wing structure outboard isn't stressed very hard because it's structurally very short. The wing goes out and says, I want to optimize a little more span. The bottom line is we had about 15% less takeoff weight, 20% more aero efficiency lift to drag, about 27% less fuel burn, and so on. And bear in mind with these numbers that this is actually a stunning reduction in structural weight, which I don't show here, but it's about 40% less structural weight. So that plus the fuel savings, of course you have fixed weights with all the seats and all the people. Those things are still there, so you can never, you can't make those go away. But there was a dramatic reduction in structural weight because it had so much less surface area and the loads were so small. This then is where the airplane evolved to next. This is an airplane that was being developed just before the Boeing merger with McDonnell Douglas. This is going to be the airplane that saved McDonnell Douglas. There were merger talks at the time with Northrop, and that didn't materialize, and much to all of our surprises, we suddenly became Boeing. But just before that, this is where we were headed in California with the Douglas Aircraft Division. And this airplane had passengers on the top deck and cargo on the bottom deck, and it was really nice. It packaged better, and its operational characteristics were more like a normal airliner. Here's a comparison of that airplane with an A380. And you can see how different it is. It actually is tiny when you look at it. By the way, look at the vertical tail on the A380. Look at that monster. All the weight and friction drag of that thing. Why? Because the engines are a mile from the center line, and if one fails, I got trouble, right? Here's the floor plan. Here's the upper deck of a 584 passenger version of the airplane. And you can see the two decks of the Airbus A380. Again, on a big double decker, I have to have very long inflatable escape chutes. It's challenging to keep those from blowing over in the wind and so forth. So having all the passengers on a deck very near the ground is really nice for safety and operations. This is what the airplane looked like just before the Boeing merger, when it was being proposed as something that could go in and be a competitor with the Airbus A3XX at the time. And you can see the numbers. Again, the empty weight of the airplane, almost 20% less. Takeoff weight, 18% less. You need one less engine. You need 3 instead of 4. And I got 32% less fuel burn per seat. So big, big savings. A lot of people ask the question, hey, if I have a blended wing, well, on a normal tube and wing airplane, they're cool because I want to make a bigger airplane. I just cut the nose off, cut the tail off, put a constant section extension in, and I've stretched the airplane easy peasy. And we're not going to do that, obviously. An airplane like this, it's an airfoil. If I cut it from the left side to the right side and try to stick something in between, it's very hard to make that smooth. What we realized, and this is my principal patent on the blended wing actually, was that if instead you plug on the center line, So you grow the airplane from the center line out, you add wingspan, wing area, and floor area all at once, and oh, by the way, it's balanced. The payload center of gravity and the lift, the additional lift, are already aligned. You get a really nice family, and you can have the outer wing largely untouched as you grow the airplane. In this case, it's showing from 350 passengers to 550. And that's what it looks like. So you can see kind of conventional structure outboard, wings, ribs, and spars. Inboard, I got these big open bays with very large ribs. This airplane was 3-engine pod mounted. So it's very different than a flying wing. It blends the payload and wing. You can look at it a couple different ways. It's like a flying wing with a very unusual chord in the middle. A friend of mine says, hey, isn't a blended wing just a flying wing with 2 taper ratios? And he's sort of right. It sort of is. But the point is that how you get to that blending and what you do with it, that's the thing. It's optimizing the aerostructural solution. Very low part count. That's the thing that excites the guys who want to build these things. So again, 30% less airframe weight, 25% less thrust, more aero efficiency, less fuel burn then, and in endurance, it's crazy. You can get a lot more endurance. So for a UAV, why do I think these are good options? Well, for the same reasons we just listed. Light, low cost, but we also get an unusual payload volume. It's flat. The payload compartment, instead of a tube and wing, it's flat. Very maintainable. It's sort of like take the lid off and lay it on my table. It looks like I was, got my Radio Shack kit of stuff, parts on it. I just laid it out flat. Very maintainable. And it's quite survivable because it's tough. It doesn't have skinny little tiny things sticking out, sprouting all over the place. The packing volume, when I look at how much volume is in the airplane compared to the swept volume of the airplane on a tarmac, it's very, very efficient as well. That said, I will say this. When you look at the pack out of a UAV, a tube and wing UAV, you take the wings off and lay them against the fuselage, it packs down to a pretty small box. Blended wings don't pack down that small. They pack down from a volume standpoint very nicely, but they usually have a little bit of a triangle shape. So that's one area where the blended wing isn't as good as a tube and wing for UAVs. So when we started the UAV, looking at it as an option for a blended wing, we had kind of an interesting notion. We said, let's see if we can make this, so flat. Could we make the airplane in 3 pieces? Because we were thinking of making many, 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 many little airplanes. And this is the three-piece airplane concept we came up with: an upper skin, a lower skin, and a payload cover. Now the lower skin, what you're looking at there is it's sort of like a tray at a cafeteria. It's got dents and divots to hold the beans and the hot dogs and keep them all separate. When I glue those together, it traps a volume in the middle that only eats up about 1/3 of the payload volume. So there's that house shape in the middle is offset from the upper skin. When I glue it all together, it traps the volume. That's the fuel tank. Then everything else is accessible, all the systems and engines and so forth under that belly pan. And that kind of depicts it. So when I glued it all together, I didn't have a separate fuel tank that I made. It was just a bump in one of the skins. I didn't have separate compartments I had to make separately. They were just depressions that fit the parts for me. And there it is. And we built that dang airplane. We wind tunnel tested it. And it flew great. And that's about the time we got the attention of Northrop Grumman, who said, this is pretty interesting. Let's collaborate with you guys. And we started the development of an even more advanced airplane. It was bigger, that would meet the needs of other users who had to carry more payload. This shows some of the flow solutions on the airplane. And for some of you who aren't familiar with fluid dynamics or computational fluid dynamics, what you're looking at are the pressures on the airplane. Red is vacuum. It's something less than the atmospheric pressure. Blue is compression. It's higher than atmospheric pressure. Green is 0 pressure. It's basically atmospheric. And you can see that the trick to the airplane, why it doesn't need a tail, is because I push down on the back of the fuselage. That's what's trimming the airplane. That's what's holding the nose up on my stable airplane and allowing me to have a nice span load shape. This is the KB4 that we tested in the wind tunnel at Swift. Again, we got great data and confirmation that the lift-to-drag performance was there. So some of you might be asking, why the heck do the winglets aim down? I don't think I'm going to tell you yet. I'll save that to the end. There's a really good reason. We'll talk about that. You guys, what do you guys want to ask me? I'll tell you. So in flight test, one of the things we were very proud of in the development of that airplane was we wanted this thing to be usable for people who didn't have a lot of resources and didn't want to have a lot of resources to operate it. This is a big airplane, you know, relatively speaking. It's a couple 100 pounds and it's carrying sizable payload and it flies for 15 hours. That's a pretty serious airplane. But we were able to pack it down. 3 airplanes fit into those boxes you see on that trailer, and the entire net system you see down below hangs on the side of that trailer. So one trailer carries all 3 airplanes, spares, fuel, and the launch and recovery system. So one trailer is the whole system with that airplane. So this is going to give you an image of why I think blended wings are especially interesting for UAVs. So you're looking at the center body. The wings have been taken off the airplane. You can see the props in the back. It's a pusher airplane. This is the airplane we developed as Swift alone at the time, actually. And then we merged again with Northrop, and then they adopted it as their baseline Class 2 UAV. So if I take the payload cover off and I look inside, there's, in this case, I've got a fuel tank in the middle. It could be left and right. They wanted to have 2 separate turrets, one on left and one on the right, so they wanted the fuel in the middle instead of on the sides. And then in front of that fuel tank and to the other sides, there's room for all the other payloads you want to carry. You can see the engine in the back. Take the skin off further, you can see the engine and muffler accommodations. And these airplanes need good muffling to be good neighbors, not too noisy. So in the what we call the arrowhead, the pointy bit in the back of the airfoil is plenty of room for nice mufflers. You can also see in the nose we have the vehicle management system where the autopilot power management systems live. The GPS equipment, you can see the 2 turrets are the circular things there with the quick disconnects, and then we've got the operator interface panel on the lower right. So when I'm setting up the airplane, getting ready to fly, it tells the operator what the voltage is in the batteries and on the bus and what the revs are and so forth. Here again is a look from the backside. Take the skin off, you can see what it looks like. So it's a very different architecture than a normal tube and wing airplane. It allows you some very different opportunities, and there's a lot of useful volume in the airplane. So I want to show you a video produced by Northrop Grumman that depicts the first flight of the Bat-12. This is up at Camp Roberts. And this is showing that their customer wanted to have a standard launcher that was used by the other services. And so our beautiful little lightweight launcher was replaced by one 4 times as heavy. But it was approved for use overseas. So there you go. So here's the airplane. This airplane had enlarged wingtips to house special antennas. And this is showing us the different software that Northrop had to identify things. And for this, some of the things that we're trying to do with the Wildlife Challenge, of course, is to be able to see things that are moving and quickly identify them more quickly than you would just looking at a screen. So there are all kinds of neat software algorithms that are going to play a big role in the UAV challenge. We hope all the competitors really emphasize that, because there's going to be gold in them Thar hills. Getting the airplane there, that's important, but extracting the data is the most important thing. So the other thing the airplane has here, so you can see, for example, kestrel motion detection. So it picks out anything it sees moving, and a little shadow coming from behind a tree or a shrub line or something just pops right out at you when you have that kind of software available. This airplane is net recovered. So it's a so-called runway independent airplane. It's interesting, some of you may know the in situ Scan Eagle family of airplanes, and they have a really nice recovery system called Skyhook, which is very, very nice. And we had a similar system for the airplane. Unfortunately, the patent at the time and they were not willing to license that technology, so we went instead with a straightforward net system. But that ended up having a lot of benefits. It treats the payloads a lot nicer than some of the other recovery systems. So that's an example of the airplane being realized as a UAV. And to wrap up here, let me just show you. I just want to show you some pictures of the X-48. So some of you are aware that NASA and Boeing, so this is after I left Boeing. By the way, in the 12 or so years that I had left Boeing, I had the pleasure of designing about 10 vehicles, all of which either raced in competition or flew and were used by our services overseas and so forth. 10 honest goodness vehicles, and that's a real privilege and amazing. And it's just tough for big companies to move fast. It took it in that same time period after I left, they finally got this thing flying. So here's the X-48, wonderful program. They've learned a ton, but it was a time-consuming program. Here it is at the Langley 30x60 wind tunnel, which no longer exists. So that wind tunnel is now gone. It's been leveled. This airplane was to demonstrate the low-speed handling qualities of a commercial jet transport class airplane. There it is flying at Edwards Air Force Base in the 3-engine sort of standard version. And then later they did an X-48C version where they looked at using end plate fins to act as acoustic shields to get even more acoustic benefits from the airplane. And there it is again flying over Edwards Air Force Base. So here's our contact information. If anybody has questions, we'd love to chat with you. Contact us anytime. And with that, I think I'm available for questions, guys.
That was impressive.
We do have some
Mark.
questions. That was impressive.
That was really impressive.
Wow.
Yeah, thank you very much. And actually, we do have somebody from NASA on, Mark Moore, who actually did a webinar for us previously on the vehicle
Mark
sketchpad.
Moore. I know Mark.
Oh, wow. Well, we should unmute Mark so he can ask some questions too, and you could say hello.
Great.
Yeah, let's see. Yeah, where's my, hey, Mark.
Hi, Mark.
Yeah. Mark, are you there?
I'm here.
Hey.
Mark Moore there.
Hi, Mark Moore. How are you?
Anyway, other questions that we have. A question about just what are you using to fasten those different pieces in your UAV together? Do you have any best practices to advise there?
Certainly. So that's a great question, actually, because it
comes from Ron.
Not easy to overlook. We almost always use quarter turn fasteners, very common in aerospace. And what that means is I can unscrew something by turning my screwdriver 1/4 turn, and I can lock it down by going 1/4 turn. They're a little expensive parts compared to a screw, but they're captive, which means that when I unscrew it, there's no way I can lose the screw. It's captive. It stays with the part. So when you make something you want to use in the field, especially if you're going to be going in and out of a part of the airplane a lot, always use captive fasteners. Quarter turn fasteners, there's all kinds of captive fasteners. You can Google them up and you'll see all the different ideas. But the point is, you're out in the middle of nowhere and you got a screwdriver and boop, you drop a screw in the sand or the dirt. Now what? The other thing you want to think about when we design our UAVs, we try to make all of the non-captive fasteners exactly the same fastener. So inside where we have normal screws and normal bolts and whatnot, we use the same fastener for all mounting. And that helps the operators quite a bit.
Okay, so quarter turn and then uniform, be uniform in the ones you use, standardize.
Mm-hmm.
Okay. Can you throw back up your contact info?
Mm-hmm.
Yeah. And then we got a question asking about the materials that you're using. What are the materials of construction?
So most of our UAVs have been built, the bats and the killer bees are built out of carbon.
Okay.
We normally use bidirectional cloth pre-preg. and you can autoclave cure it, or now there's some great non-autoclave systems, and that's a really good way to go. Autoclaving is expensive. Autoclaving applies more pressure, and it does make the system higher performance, but it is costly. So out of autoclave is where the industry is headed, and there are many good epoxies now. So you stack up your layers of cloth, you put a piece of plastic over the top with a vacuum hose, you suck it down so you got 1 atmosphere of consolidation pressure. Cook it in a simple oven, no pressure. Yeah, so instead of doing it the Kentucky Fried Chicken way, you just do it like you would at home. You put it in an oven, and then the epoxy kicks off. It converts its state. All these broken chains link up, the ends link up and lock it up, and that's what the curing is. Now I've got a solid part. Fiberglass is much less expensive, not as strong, not as stiff. But the nice thing about fiberglass, especially if you get E-glass, not S-glass. S-glass is structural fiberglass. E-glass is electronic fiberglass. E-glass is almost as strong as structural fiberglass, but it's electromagnetically transparent, so your antennas will work. If you make your airplane out of carbon, you got to be real careful where the antennas are. So all of our UAVs had E-glass winglets where the antennas lived. So the antennas were all inside an electromagnetically transparent material, which is E-glass.
Mm. Our last webinar was on RFID tags, so that's actually a very timely statement you made.
Hey, I have a question.
Yes.
I know what the design that you did included a fuel tank, but now if we were looking at using batteries, what kind of, I guess, endurance are we looking at, and what are we taking away from the weight of that? And I guess it would depend on how much you would use. But can you kind of talk about the comparison between the two, please?
Sure. So batteries are improving so fast, but of course they're really still not there to compete with gasoline or diesel fuel, kerosenes and whatnot. We're still off by a factor of 10 or so. So you're not going to get day-long endurance with batteries with anything close to the payload weight that we carry today. So if you had 2 airplanes of equal size, one with batteries and one with gas, the payload difference, and you tried to match the endurance, of course, at some point the batteries will never get there. But let's say you do a day-long endurance, which is very tough with batteries. You would have a very minute payload fraction, and that's why you just don't see them used for high endurance. That said, if you're talking a couple hours, which is very useful, it can be done, and you can have a useful payload fraction. So when I say payload fraction, I mean how much payload weight do you have as a fraction of the total weight? And 15% payload fraction is pretty common for a long endurance airplane because you got a lot of fuel. With batteries, it might be tough to get 15% and have good endurance. But so you've got a couple issues. One is for the types of things we're trying to do here, we don't want to use what are called primary cells. So there's a type of battery that's awesome. It's called a primary cell, and it's a single-use cell. So you can get lithium-ion-like or lithium-based batteries that are primary batteries, and they'll have twice the performance of the rechargeables. But as a practical matter, I don't think that is a good solution for this competition or this type of mission because you want to use these over and over and over and over again. That would be very costly. So my hope, I think fuel cells, when they come aboard, that'll be the end of the internal combustion engine. When we really get fuel cells light enough and that can eat almost anything, and there are fuel cells that can eat gasoline and eat other types of fuels and make electricity, that's going to be fantastic. And the reason is not just because I get the energy density of gasoline again, but one problem with batteries we don't talk about much is that the batteries I launch with are the batteries I land with. On a 747, it takes off with a bunch of gas and lands at about half its takeoff weight. So its average weight over the mission is way less than its takeoff weight. So on gasoline systems and other carbon fuel systems, As I use the energy, I throw the weight overboard. On batteries, I use the energy and I keep lugging that good for nothing, no good discharge battery is still on my airplane. So so you're stuck with that. And that is some of you who are familiar with the Breguet range equation from school. There's a Breguet benefit to consumable fuels that you don't get with batteries. But some of you might get clever and say, but maybe I could do something different. Why can't I throw some of that weight overboard? So give that a little thought.
I don't know if we want to advocate people just chucking their batteries mid-flight.
not living in a reusable, recyclable, and responsible way. Yeah.
Yeah, I think me and Mark had that discussion.
Yeah, that's right. So there's some possibilities out there. It depends on the mission.
Yeah, you could put a parachute, a tracker on it, I guess. But yeah,
there you go.
That's a good point. I hadn't made that connection, but it seems so obvious as you're mentioning it. Like, yeah, that does affect things.
Why not a flyback battery?
Yeah. Can we ask you a theoretical question just about definitions of drag? There was a question actually that Ron asked a little while ago, asking about induced drag. You're talking about vortex drag. Can you talk about some of the, could you define induced drag for us?
Absolutely. So I mentioned a bit ago that airplanes, this is a very classical result for when you look at airplanes. When they're flying at their point of max efficiency, that's when their lift divided by their drag is maximized. At that condition, it's half of your drag is what we call parasite drag, which was mainly friction drag, and half of your drag is induced drag. We call it induced drag because it's lift-induced drag, and here's the problem with lift. Lift leaves vortices in the wake. So when I make lift, I deflect the air, and when I do so, I leave energy in the air due to deflecting it. That's lift-induced drag, and the evidence of that is the vortices in the air. So you've all seen airplanes making landings, and sometimes you see kind of a white, wispy tube coming off the wingtip. They're not dumping fuel. That's the wingtip vortex. The high-pressure air under the wing is whipping around the wingtip to the vacuum on top, and it makes it spin. It makes a little tornado that is behind the airplane for miles. They actually last for miles and miles and miles. And in that vortex, the air is going very, very fast in the middle. The pressure drops, the temperature drops, and the water vapor condenses out into water droplets that reflect light. And so you see them. And so there you can actually see the vortex drag. All that energy that was left in the air came from somewhere. Well, guess what? It came from you and your propeller. You had to make energy to drag the airplane through the air and make that lift. So lift-induced drag, is the same as vortex drag in that terminology.
Okay, yeah. There we go. That's the question. There you go, Ron. They are analogous.
Yes.
Question from Raj for you. Will the winglets act as a vertical stabilizer also, or should, actually just reading his question, or should we stick with decontrol surfaces?
So on a blended wing, because we sweep the wing for pitch stability and control, that places the wingtips after the center of gravity of the airplane. So it's a great place to use to add winglets to double as fins. So the airplanes that I showed you today, we do that. So those winglets on the tip, we just talked about vortex drag or induced drag. Winglets reduce that because they make the airplane appear to have more span. And I should have mentioned that before. The thing that reduces friction drag or parasite drag is small wetted area, surface area. The thing that reduces vortex drag is big wing span, which is why gliders have big wing spans. And that's why blended wings are really cool, because they reduce the wetted area, and now since the wing structure is so much lighter, I can stretch it out further and get more span. The whole system just feeds on itself, and I can get more lift-to-drag ratio. So I've taken a bird walk. I've lost the original question.
Basically, asking you how do you stabilize it vertically? I mean, that's kind of what you're.
There you go.
Yeah,
so the winglets. So winglets reduce vortex drag, and so that's a good thing. So putting the winglets on, okay, yay team. Now I can use them since the wingtips are after the center of gravity. That winglet can act as a fin to provide directional stability. Absolutely, yes. And that's a great two for the price of one.
Well, I'll make it a three-fer. I mean, you mentioned earlier that there's a reason why your UAV had the fins upside down. I mean, is that a
That's
center of
right.
gravity thing too? Yeah,
It's
I don't know the answer.
actually
What is the answer?
so the answer is the reason winglets reduce drag. There's all kinds of ways you can explain it, but here's one way to explain it. I mentioned before that if I don't have a winglet, high pressure air on the bottom of the wing comes whipping around the wingtip into the vacuum on top. Okay, so if you imagine above the wing there's an inflow, and below the wing there's an outflow. If I stick a fin straight up, it's just like a sail on a sailboat.
Yeah.
If I get an airflow component to my side, I can make thrust. I can push forward, just like a sailboat does. Sailboats take wind from the left or the right, and they deflect it partially aft, and then they get thrust. Well, winglets are also sometimes called tip sails. So the winglet literally is thrusting. So if I were to cut the winglet off and bolt it back together with a force gauge in between, I actually measure a thrust on the wingtip. Now, am I getting something for nothing? No, I am not. The total airplane still makes drag. It just makes less because the winglet is contributing a component of thrust. Well, since it's contributing thrust, if I put the winglet below the wing, it also holds the nose up. And for those of you who are airplane geeks, you know that for airplanes that are statically stable, airplanes that are naturally stable without a computer helping them in pitch, they end up having a nose down moment. There's a torque that has to be balanced. I normally balance that with the tail. On a blended wing, I balance it with the aft part of the center body by pushing down a little there. But if I have the wingtips thrusting forward, guess what? That also pulls the nose up. So I get some free trim.
Makes sense. It's very clever. How'd you come up with that? You just tried it? You're like, let's just flip
No,
these things, see what it does?
So I wanted to do it for years. So it's funny how things go in the industry. You see winglets on all the airplanes out there in the world, right?
Uh-huh.
But winglets work much better going down than they do going up for one simple reason, and that is that on the upper surface of the wing, I've got at cruise, the flow, many of your listeners may not know this, I'm flying around at maybe 80% of the speed of sound, but on top of the wing, the flow is supersonic. The wing, the way it makes lift is by accelerating flow on top of the wing and decelerating the flow on the bottom. Decelerating the flow on the bottom makes high pressure, accelerating it on the top makes low pressure, the difference lifts the wing up. So I got supersonic flow, and by golly, it goes supersonic, and then it slows down through a shock wave. So you got supersonic flow and a shock wave on the wing the whole time you're flying to Grandma's house. So so all that supersonic flow on top, if I now take my wing, supersonic flow on top, and I bend the wingtip up to make a winglet, I'm getting supersonic flow superimposed on supersonic flow. I can get nasty action in the middle. If I go this way, then the super velocities, we call them, don't add up so badly. I get some relief. So it's a much better way to do it. Of course, then my winglets hit the ground. When I land in a crosswind and I flip a wing, I knock the wingtips off. That's the only reason they go up on jetliners is that. Otherwise, the natural direction is down anyway.
Be down. So because you're catching the thing, that's how you're able to get away with it.
Right.
So
Exactly.
so if we're gonna have designs that we want to actually land, we should stay away from that.
Well,
Yeah.
so some of you guys should Google Ewald Schuster, Schuster, blended wing body jet, or maybe it's Killer Bee jet, KB jet, and you'll see the landing gear architecture I designed for Ewald, and he took our Killer Bee, put a jet engine in, and it has the winglets are the landing gear, they're the wheels, and there's a main wheel in the nose. And you guys might say, wait a minute, that's madness, that's craziness. If you put landing gear in the wingtip, you're going to snap the wings off on landing. And again, it's one of those things that doesn't make sense at first, but the truth is, when you put wheels in the winglet tips and put a big wheel in the middle, the nose wheel is actually the main gear. What you really have are two very lightly loaded tail wheels on the wingtips. So when I land, I've got the nose gear, if you will, the main gear in the nose, is very near the center of gravity. It bears most of the weight of the airplane. The wingtips are not carrying much load, so even if they hit first, the airplane just pushes out of the way because it's not reacting any load, any inertial load. So that thing works great. And someday I want to make a general aviation airplane that does that.
Hmm. Other questions, guys? Let's give him a second.
Did you ask? Did you already
Yeah.
ask all the questions? Because it seems like sometimes I'll get these questions in, sometimes we won't. Uh,
Let's see. I don't think I missed any of them. But here's a question about Raj. I'm sorry. So the question is, in these mentioned drone flights, can VTOL be achieved? Sorry, I can't remember what VTOL means.
Vertical
Uh,
takeoff and landing.
oh, sorry. Thank you.
That's okay. I have those
Sorry,
notes.
guys. It's easier just for me just to ask than bluff.
So with our UA, so every time one of our customers would go to a radio control flying club and watch some guy hang his airplane on the prop and just hover in front of him with a normal airplane hanging on the prop, they'd come back and ask, why can't we do that? Why can't we take off and land vertically? And of course the answer is you can. You put an engine big enough. The radio control guys, of course, cheat because the airplane is all engine. It doesn't carry any useful load. And the engine is colossally giant and burns fuel like mad. So it turns out that if you wanted to do VTOL on the little teeny propeller, it's a disastrous idea. Actually, by the way, I don't want to be controversial, but a lot of the guys are probably thinking about quad rotors, and quad rotors are actually terribly inefficient unless those individual rotors are very, 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 very large. The quad rotors we all see today are impossibly small. So all of the efficiencies, so those of you working on quad rotors and getting the VTOL benefit, which is wonderful, VTOL is fantastic, but then you have to pay for it when you're en route and in cruise and holding yourself up. The energetics are poor. In fact, they're terrible. So the only way you can improve the energetics is to reduce the disk loading, and there's some classical relationships you can find on the internet that show how, if I have 40% more prop diameter and I got double the disk area, then the power I need to drive that comes down dramatically, maybe comes down 35% or something. So take a look, and propellers are light, make them big. The little ones are easy because they're cheap and they're available, but do the math and figure out how to do big props. So VTOL on a blended wing. If you put a fan in the middle of the body, terrible idea because you're taking all the real estate that you just paid dearly for to carry the good stuff. If you want to hang the airplane on the prop, you can do it, but again, you end up with an engine. Typically for VTOL, the engines would have to be between 5 and 7 times bigger in both horsepower and weight to hang the airplane on the prop with the useful payload. So that's nasty. When you think about airplanes are typically also about 15% of your weight is typically propulsion, the motor itself, not the batteries, and 15% your payload. Well, if I'm going to take that 15% that was propulsion before, multiply times 5, you can see I'm getting into trouble. It's a lot of weight. So,
final question. Have you tried bungee launching your devices before?
We have.
Would you advise it?
But bungees are great. Just be aware of this, though. A little known thing, it turns out that the Army originally deployed the, what was it called? It was the, well, it doesn't matter. There was an electric UAV that was used for quite a few years where one person held the airplane and it had a hook in the nose and it hooked to a bungee, and another guy stood about 12 feet away. They stretched that bungee out, held the bungee up in the air, and they shot it, right? And believe it or not, there were actually very serious injuries from that.
Oh, I bet.
Awful injuries. So like you would never imagine could be possible injuries. So if you do a bungee, do it like a high start. Google high start, HISTART. That's what the glider guys do, the competitive glider guys do. And basically, it's a stake in the ground with a rubber band. You stretch it out, and you let go of the airplane horizontally. And yeah, you need a longer rubber band, but it works great.
All right. Mark, this has been a lot of fun. Are you going to come with us to South Africa? You should, if
I
you
would
aren't
love
planning
to.
already.
I would love to.
You need to
So,
come.
all right. Well,
Uh,
all the best to your team
uh,
members and all the listeners.
yeah, thank you so much for taking the time to be with us today. And for everyone else, Princess Leia, do you have any closing remarks on
I
kind of next one and
sure
general
do.
stuff in the world of the challenge?
Absolutely. I do want to thank Mark again for his great webinar. I think it was very, very, very helpful. And I think, teams might find it to be pretty useful if that is a route that they're looking at getting involved in. Now, can you see my screen or
Nope.
are we still sharing
You
Mark's
need to present.
screen? All right, let me change that real quick. Okay. What about now?
Yes.
You can see my screen.
No. Presenter
Oh, I can
here.
see you. Yeah.
Here, you're the presenter now. Hit play.
Yes. All right, there we go. All right, for those of you that don't know, our critical design review is out with details. June 30th is when it's due. So make sure you go to Teams, Critical Design Review, and review this. If you have any questions, go ahead and send me
Mm.
an email. But we're out all the details that you need for this tough challenge. Now, there's one thing I do want to add. AIAA has their SciTech conference January 2015, and they're allowing us to have anywhere from 4 to 6 of our teams present in their engineering design papers. So what we need to do is we need to submit to them by June 2nd. I've been working with them to see if we can get an extension from them because I know our design reviews are due on the 30th. So hopefully we'll get that extension, but if we don't, we'll need the teams that are interested in presenting at their conference to actually send us the call for papers or the paper that you're interested in submitting for this, which is pretty much your design that you're doing for the challenge, and send it to us by the 30th of May. And then what we'll have to do is see if we get 6 papers from you guys, great. We're just going to go ahead and forward those to them. But if we get 10 or 20 or 30, we will have to evaluate those internally and then pick the top 6 and submit them to AIAA. But here's the details for what you would need for your paper. So if you are interested, go ahead and go to this page and look at it and see what the requirements are. I am, like I said, working on a deadline to see if we can wait to submit ours until after our critical design reviews have been submitted by the teams. So if you guys can go ahead and check this out if you're interested, that would be great. Design reviews are available. And other than that, next week I will be at the AUVSI conference. And if you or your team members or anybody from your organization is attending, please make sure you send me an email at director@wcUAVc.com. And that way I will schedule some time to meet with you. We are trying to work with some of the media to see if we could do some interviews with any of our teams, especially if it's our local Florida team. That would be fantastic for you guys to actually meet with our publicist in Florida, and he'll work with you to promote the challenge, but also what your team is working on as well. So that's the email. Send me an email if you guys are planning to attend the AUVSI conference. I'll be there from the 12th of May until the 15th. So pretty much the entire conference. I think that should be it for me. Unfortunately, our South African director is not on today, so we won't be able to have our news on the ground, but I know that he is working hard in trying to get the information that we need for CAA approvals for flight and everything, because I know that's been a critical issue in South Africa. So keep in mind that we're working on that. And for the challenge, should not be a problem for us to actually fly because we are flying in private property, but also working with one of the national parks to see if we will need the extra space to fly with them. Any other questions?
Toby had some comments, but I think we can kind of take them offline.
Okay, all right. Well, that sounds
Okay.
good. All right. Well, thanks
Okay.
again, Mark,
You
for a
bet,
great
guys. Take
presentation. I
care.
appreciate it.
All right, guys. Well, everyone, have a marvelous week, and we'll see you on the next one. Mark, thank you again. That was a lot of fun. And take care, guys.